Welcome to AITV News. Today we're exploring the breakthrough that earned three United States-based scientists the 2025 Nobel Prize in Physics and pushed quantum mechanics from the realm of theory into technology we can hold in our hands. The prize goes to John Clark of the University of California, Berkeley, Michel H. Devoret of Yale University and the University of California, Santa Barbara, and John M. Martinez of the University of California, Santa Barbara. The Royal Swedish Academy of Sciences honored them for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. That description may sound dense, so let's unpack it. First, quantum tunneling. In everyday or classical physics, a ball without enough energy to roll over a hill simply rolls back down. But at the quantum level, particles behave like waves. There's a small but real chance that a particle can appear on the other side of the hill without ever going over it, essentially sneaking through the barrier. That improbable shortcut is called quantum tunneling. Until the mid-1980s, tunneling had only been observed in subatomic particles. The new laureates asked a bold question: could you make a human-scale device behave the same way? Working separately, yet along parallel lines, they built tiny superconducting circuits, still large enough to hold, that acted as single quantum objects. In those circuits, they observed both energy quantization and true quantum tunneling. It was the first time anyone had proven that quantum rules apply, intact, to engineered systems we can see. Why does that matter? Because it bridges the microscopic quantum world and our macroscopic one, turning abstract physics into practical hardware. Once you can coax quantum behavior out of a circuit, you can start designing machines that exploit it. The most talked about application is quantum computing. Qubits, the quantum counterpart of bits, can exist in multiple states at once, allowing certain calculations to run exponentially faster than on classical machines. John Martinez later led Google's Quantum AI Lab, which uses concepts rooted directly in this Nobel-winning work. Quantum mechanics could also revolutionize communication and sensing. Quantum cryptography promises theoretically unhackable messages, while ultra-sensitive detectors may transform fields from medical imaging to geology. One such device, the SQUID, short for Superconducting Quantum Interference Device, was pioneered by John Clark. A SQUID can measure magnetic fields millions of times weaker than Earth's, making it invaluable for brain scans and prospecting alike. The Nobel call still came as a surprise. To put it mildly, it was the surprise of my life, Clark told the committee, quickly crediting his co-laureates as brilliant people. Their collective achievement shows that the marvels of quantum theory are not confined to textbooks or particle accelerators. They can be engineered, switched on, and measured in the lab. By demonstrating macroscopic quantum tunneling, Clark, Devoret, and Martinez have laid the foundation for technologies that could shape the coming decades. Unprecedented computers, secure global communication, and new ways of probing the human body and the planet itself. The era of practical quantum technology is no longer science fiction. Thanks to this year's Nobel Prize winners, it has already begun.